So here we have another proofs video. So in this video I'm going to show you 3 proofs which correspond to some of the statements we saw about the eigenvectors of special types of matrices. So once again, I know some students don't really like proofs, they don't enjoy them, and others really enjoy them. But if you are a first year math students, it's unavoidable that you have to see some proofs. So let me prove that all the eigenvalues of a Hermitian matrix are real. Okay, so that was stated here. I'm going to prove this arrow here. Okay, if A is Hermitian, all the eigenvalues are real. This proof is quite concise. So let's start with the definition of an eigenvector. A times eigenvector B is equal to the eigenvalue lambda times the eigenvector B, by definition of eigenvector. Next we do the Hermitian conjugate or the dagger operation on both sides. Okay, so we have that A times V dagger is equal to lambda V dagger. Next, we apply the property that the dagger operation, so you remember you have 2 matrices A, B, and you do the dagger operation, this is equal to B dagger times A dagger. So you had to swap them around, yeah? And also the dagger operation, if you have lambda times matrix A and you do the dagger of that, that's equal to lambda complex conjugate times A dagger. Okay, so those are properties of the dagger, of the Hermitian conjugate. So you apply those properties, and what do we get? We get that V dagger times A dagger is equal to lambda conjugate times V dagger. You might be surprised here to see a vector multiplying a matrix on the left, because that's not usual, right? But this is V dagger. So if V normally was a column vector, so if here we had, let me change colors. If here we had a matrix, maybe a 3x3 matrix, times a vector which is a single column, then here on this side now we have a vector which is a row vector, because it is the Hermitian conjugate of the column, so it is a row, times a matrix like this. And this multiplication can be done, and the result is a row vector. Okay? Excellent. The next step is to multiply both sides by V. So let's do that. So this means that V dagger times A dagger times V is equal to lambda complex conjugate times V dagger times V. Okay? Now apply the fact that A is Hermitian. Okay, so that was our starting point. We want to prove that all eigenvalues of a Hermitian matrix are real. Yeah, we want to prove this arrow here with this arrow here. Therefore, it's valid for us to assume that this is true, because we try to assume that this is true to prove this. So we assume A is Hermitian, and remember that the Hermitian matrices have this condition: A equals A dagger. So A is Hermitian means that A equals A dagger. And therefore, V dagger times A times V is equal to lambda complex conjugate times V dagger times V. And now next, notice here that we have A times V. But A times V is equal to lambda times V, because V is an eigenvector. Okay? Therefore, we have that V dagger times lambda times V is equal to lambda complex conjugate times V dagger times V. And remember that when we multiply a row times a scalar times a column, the scalar can move around, yeah? So we could place the scalar on the front. So actually, let's do that. Lambda times V dagger times V is equal to lambda complex conjugate times V dagger times V. Okay? And this must be true for every possible eigenvector, but what is clear here is that if we equate the left with the right, and these two are equal, then lambda must be equal to lambda complex conjugate. And therefore, lambda must be a real value. which is what we wanted to prove. Okay, so that's the first proof. Next, another proof. This is a bit more involved, but I think even more elegant and more surprising. So we are going to prove that if a Hermitian we are going to prove that a Hermitian matrix has n orthonormal eigenvectors. So we are going to prove this. We are going to prove that if we start here, we end up here. Okay, so we are going to prove an arrow that does this. I'm not going to prove the more general case of A being normal implying this, because the proof is a bit more complicated. Also, I'm going to prove it with a caveat. I'm going to assume that all of the eigenvalues are different. If you do not assume this, the arrow is still true. Okay, this is true always, even if the eigenvalues are degenerate. But it's much more difficult to prove, and it's actually proven in the recommended textbooks. But let's do the proof assuming that all of the eigenvalues are different, which is slightly easier. Okay, so we are going to start with these two equations that I'm calling A and B. And these two equations are simply the definition of eigenvectors. So we are going to consider two different eigenvectors, Vi, associated with an eigenvalue lambda I. So this is one eigenvector with one eigenvalue, and this is another eigenvector that is different from the first. Yeah, so Vj with an eigenvalue lambda j. And by definition of eigenvectors, these two equations must be true. Okay? So to A, we are going to apply the dagger operation. So we are going to do the Hermitian conjugate. So we get that, remembering the same as before, that AB dagger is B dagger times A dagger. So let's do it in a single step. This is equal to Vi dagger times A dagger. And then on the right, we get that this is equal to lambda I complex conjugate times Vi dagger. Okay? Next, we are going to multiply both left and right hand side times Vj, which is the other eigenvector. So by doing this, we find that Vi dagger times A dagger times Vj is equal to lambda I complex conjugate times Vi dagger times Vj. Okay? And this I'm going to call equation 1. Now next, let's go here on the right to the definition of eigenvector for a vector Vj. And we are going to simply multiply by Vi, but on the left. Okay, we are going to multiply by Vi on the left. By Vi dagger, sorry, because if we want to multiply this, so this A times Vj is a column vector, so we can only multiply it by a row vector. So we are going to multiply by Vi dagger, which is a row vector, and we are going to do that on the left. So we end up with Vi dagger times matrix A times vector Vj is equal to Vi dagger, so we can keep the lambda, which is a scalar, we can keep it in front, times Vi dagger times Vj. Okay? And this I'm going to call equation 2. And next, what I'm going to do is, I'm going to subtract equation 1 minus equation 2. So 1 minus 2, this is equal to, so on the left hand side, let's subtract 1 minus 2. Vi dagger times A dagger times Vj minus Vi dagger times A times Vj. And this is equal to the subtraction of the right hand side, which is going to be this minus this. Okay? So what we can do is we can factor out these vectors and leave the scalars factored like this. So this is going to be lambda I complex conjugate minus lambda j times Vi dagger times Vj. Okay, we have arrived at this equation here. Next, we are going to factorize the left-hand side. So notice that these two terms, this one and this one, they are both multiplied by Vi dagger on the left, right? So therefore, we can factorize Vi dagger on the left times what remains. But also, they are also multiplied by Vj on the right. Therefore, we can factorize Vj on the right. And what is left inside? We get a dagger minus a. Okay, so we just factorized v1 dagger on the left and Vj on the right. At the same time, we know that lambda I conjugate is equal to lambda I, because we just proved that all the eigenvalues of a Hermitian matrix are real. Therefore, the complex conjugate of the eigenvalue is equal to itself. So therefore, this is equal to lambda I minus lambda j times vi dagger vj. Now, if A is a Hermitian matrix, remember the definition of Hermitian matrix, A equals A dagger. So this means that this here must be 0, because A dagger minus A must be equal to 0, okay? So therefore we have that lambda I minus lambda j times vi dagger times vj is equal to 0, okay? Next, do you remember that a vector dagger times another vector was equal to the inner product between both vectors? So I remember I showed you this earlier in the course. So vi dagger times vj is equal to the inner product between vi and vj, but actually the inner product in the physics convention. Okay, so therefore we arrive at the fact that lambda I minus lambda j times the inner product between vi and vj is equal to 0. Okay, so this must always be true for any two eigenvectors vi and vj, and for any two eigenvalues lambda I and lambda j. So now you can see that if lambda I is different to lambda j, so different eigenvalues, then this means that this is not equal to 0. So then this means that this must be equal to 0. Which means that vi and vj are orthogonal. Beautiful proof. And if they are orthogonal, knowing that every eigenvector can be scaled up or down arbitrarily, you can always find a scaled version of the vector that has unit length, and therefore they can be made orthonormal. Okay, and this applies to any two eigenvectors that have different eigenvalues, as long as the matrix is Hermitian. Okay, so in conclusion, all of the eigenvectors are orthogonal to each other, and therefore, so vi and vj can be any two. Can be any two eigenvectors. So they are all orthogonal to each other. So therefore they form an orthonormal basis. They form an orthogonal basis, and if we normalize them to have unit modulus, then they are orthonormal basis. Okay, so that was the proof that a Hermitian matrix has n orthonormal eigenvectors. Next, let's prove that the eigenvalues of unitary matrices have a unit modulus. This one is a bit shorter. When we studied unitary matrices, we know that unitary matrices fulfill the fact that they preserve the angles and the lengths of vectors. And actually, you knew that a matrix A times vector V inner product with the same matrix A times some other vector W is equal to the inner product of vectors V with W. This was a property of unitary matrices. Okay. In particular, if V equals to W, then we get this, which means that the norm of A times V squared is equal to the norm of V squared. And that's what I said about unitary matrices, that they preserve the length of the vectors. So if vector V has a certain length, the vector A times V has the same length. Okay. So now apply the definition of eigenvectors. So the definition of eigenvector is that A times V is equal to lambda times V. Okay? But if we apply the norm to both sides, the norm of A times V must be equal to the norm of lambda times V, which is equal to the norm of lambda times the norm of V. Okay? But now if we substitute the fact that the norm of vectors are not changed by a unitary operation, by a unitary matrix, this means that the norm of V must be equal to the norm of lambda times the norm of V, which means that the norm of lambda must be equal to 1. By the way, I made a mistake here. This is lambda is a scalar, so you don't calculate the norm of a scalar, you calculate the magnitude of a scalar. So the complex amplitude, yeah? So sorry, I should have used a single line, not a double line here. So we prove that the complex amplitude of each eigenvalue has to be equal to 1 because the matrix is unitary. So you have seen these 3 examples of proofs. They are quite elegant, they are also relatively long, and the typical question I get from students is, how do I know I have to do this step to apply the dagger and multiply Vj? Well, that's the magic of proofs. You don't know until you try. So that's why proofs are usually very, very difficult problems.